All right, so guys, you're welcome to another class. Today I'll be dealing with the electric field, and I will expect that you pay rapt attention. You take notes and pay quality attention. That's all I'll keep saying. I'm gonna take you straight up to my whiteboard right now. Yeah, I'll call it my whiteboard for now, where I'm going to be explaining concepts. Yeah, let's go there. And so here we go. The electric field. The electric field is what we'll be dealing with today. Please make sure that you are paying attention to that. Electric field. I'm going to quickly define that as this is the region of space which surrounds a system of electric charges. So the region of space which surrounds a system of electric charges. I'm going to give a spice to that definition. Most of the time, when we're defining gravitational field, we said this is the space around which, that effect of gravity is felt. The gravitational force takes effect. So in similar vein, when we're referring to the electric field, we say this is the region of space which surrounds a system of electric charges, or we say it is the region where the force exerted by an electric charge is experienced. So is experienced in an electric field. So electric field quickly states that it is a vector quantity. So the same thing with gravitational field. It is a vector quantity, and the direction. Take note that the direction of an electric field is determined by using a test charge. A test charge is normally a small positive charge. So keep that in mind, a small positive charge. So that's normally the test charge as it relates to electric fields. I'll quickly, in this class, we're not wasting time, we're just hitting the nail on the head. The next subtopic is fundamental law of electrostatics. Electrostatics. There is a law of electrostatics, and this is very common where we say like charges repel. Is a law of electrostatics. Like charges repel, and unlike charges attract. That's the simple law of electrostatics. And in this place, I will quickly draw the negative charge. The negative charge has this feature of, the electric field lines, they point inwards. In the negative charge, the electric field lines point inward, and in the positive charge, the electric field lines point outward. So keep that in mind. The electric field lines point outward. So if you bring a negative charge close to a positive charge, what happens is that the electric field lines now look like this, because the ones from the positive, they point outward. So they point outward. So and then the negative charge is receiving them. So because in the negative case, they receive, like the electric field points inwards, and this one, the positive charge seems to diverge. Electric field lines converge here, and electric field lines diverge here. So when you bring them close, that's where the principle of electrostatics, it takes effect very well. So it appears to be that this guy is, being attracted this way. Meanwhile, the other field lines look like this, understand? Because, they go out. Why this one, the other field lines look like this? Because they come in. So that's how the relationship is. And so we say there is attraction. So let me write it this way. Call it attraction between two unlike charges. So keep that in mind. That is a very important principle that you cannot overemphasize in physics. I'm now quickly going to the subheading. I'm now quickly going to go to the subheading electric force. And therein I will also consider Coulomb's law. Yeah, I'm going to talk about Coulomb's law too under this subheading. So electric force and then Coulomb's law. It has been pointed out that like charges like charges repel and unlike attract. We've already established that. So then we're now going to talk about Coulomb's law straight up. And this way, in Coulomb's law, you will see me say something about the force. Coulomb's law states that let me before I state it. Oh no, after I state it, I'm going to draw the diagram that expresses it. It states that in a given medium, the force of attraction, or repulsion between two charges is directly proportional to the product of the two charges, and inversely proportional to the square of the distance between them. So the idea here is that in the Coulomb's law, we're assuming that if we have a positive charge here and we have another positive charge here, and we call this one Q1 and we call this one Q2, the force here is directly proportional to the product of these two charges divided by, let's say the distance between them now is R, divided by the square of the distance between them. Now, let me quickly note that in physics, we have something called inverse square laws. And you will see a similarity between the law, the gravitational law, the particular law we gave in the when we are considering gravitational field. There was this law we gave where we said the force is directly proportional to m1 m2 over r square. And then for gravity, we later said F equal to G m1 m2 over r square. Yeah, this particular law had a name there, and that was Newton's law of Newton's law, the one of gravity, and then we postulated this, and we observed something. There is always this over r square. In physics, we call that inverse square laws. So we can say Newton's gravitational law or you can go back and get the exact name of that guy. And also Coulomb's law too. Coulomb's law fall under that, that particular segment of inverse square law, because what we are going to look at, this one was when we are dealing with, gravitational field. This one we are dealing with gravitational field. So now we are dealing with, electric field, and then we have already established this just now, that the force is directly proportional to the product of the two charges and inversely proportional to the square of distance between them. So we can quickly now write, like I used to say, you now quickly introduce the constant of proportionality. So here we introduce the constant of proportionality, we now change this guy to equal to. So it now becomes equal to, and here in electric field, the constant of proportionality is K. So we have K Q1 Q2 over R square. And so we now establish what K is. So this is actually the Coulomb's law. So, but we can establish and say K is equal to 1 over 4 pi E naught, where E naught is called permittivity. Please, you are new to this, so don't take it as something that you ought to know before. It is teaching. That's why we are in class. So write it down and say, oh, I'm learning. It's new. You didn't see it in your dream before. So write it down, and that's why you're in class, to learn it. So you have the formula here. This is K, and so permittivity of free space, and that's E naught, and it is given, it's a constant. So E naught is 8.85 times 10 raised to power minus 12, farad per meter. So keep that in mind. So that's the value for E naught. So keep that in mind. We can also, decide to, find another unit. We can calculate another unit for it, but we can do that together later on. But for now, let's leave it as this, farad per meter. But let's now introduce that K into the formula. We now have F equal to 1 over 4 pi E naught Q1 Q2 over R square. So this is what you have for your Coulombic force. So keep that in mind. And there is another thing. Let's quickly consider another subheading. But before we consider another subheading, as we said, we can decide to calculate the unit of E. Or let's talk about units. If you talk about charge Q, or Q, the one we wrote as Q, the unit of charge, because charge is equal to IT, as ampere times time, ampere seconds, or we call it coulomb. So don't forget, this is the unit of current is ampere, the unit of time seconds, then we call this, coulomb. Q equal to 80. So that's how charge works. So if we say force now, force in Newton equal to 1 over 4 pi E naught, and then Q1 in coulomb, Q2 in coulomb over R square in meter square. By the time we focus on unit alone, we have Newton equal to 1 over, we can leave, we can remove the constant. Whenever we are focusing on unit, we can remove this 1 over 4 pi E naught. You can have 1 over E naught now. And then we are seeing coulomb times coulomb give us coulomb square over meter square. Now, the goal is, yes, I want to show you another unit for E naught. So if we make subject of formula, if we cross multiply, C square over E naught M square. If we cross multiply, we are having E naught M square Newton equal to coulomb square. So E naught unit now is coulomb square divided by meter square Newton. So we can say that E naught is 8.85 times 10 to the power of minus 25 coulomb square per meter square per Newton. So we can, any way we choose to write it. So that's how it works. So just keep in mind that you can always manipulate your formulas to get your units. So let's now quickly talk about the concept of relative. Let me write that word very well. relative permittivity, and that is it is written like E subscript R. Now this old E, capital E that you see I'm writing here is not written as capital E, it's written as like epsilon. So like bended curvy E. So that's what permittivity looks like, curvy E. So like bended. So it bends in a way. So keep that idea in mind. So because relative permittivity now has the formula of epsilon R equal to epsilon M over epsilon naught. So it's like epsilon M divided by what? Epsilon naught. So we can say it is the ratio of permittivity of the medium, to that of air. So because we have already identified epsilon naught up above here, we have identified it as permittivity of free space. Free space means free space or vacuum or air. So that's how it works. Please, so keep all of that in mind. And let's now go straight to the next subtopic, which is electric field intensity. Electric field intensity, or some people call it electric field strength. Electric field strength. So keep all of that in mind. And it's represented with a capital E. That is the exact representation in physics. So let's define this. This is, or let's not use this. Let's say electric field intensity at any point, electric field intensity E at any point in an electric field, is the force experienced by unit. Most of the time in a concept of electric field, we don't use just a unit charge, we say a unit positive charge. So a unit positive, not just charge, test charge, a unit positive test charge at that point. So it is the force experienced, let me underline that in red, by unit positive test charge at that point. So it is a vector quantity. It is a vector quantity, and the SI unit is Newton per coulomb. That is, the idea is that the formula for electric field E now is force over Q. So that's where you get Newton per coulomb. So please take note of this formula: electric field, force over Q. So the idea here is that if we have this now, once we have electric field to be force over Q, it means we can write, we can plug in, let me be giving equation, let me be calling these equations by, let me be giving them labels. Let's call this one equation. Go back to your first formula we had for force. Let's call it equation Roman figure 1. So let's now call this one that we have here equation Roman figure 2. We can say substitute equation Roman figure 1 into equation Roman figure 2. And the meaning of that is that now we now have E equal to, I'm putting that F, value for F. Roman figure 1 contains F. So I'm putting that value for F, which is 1 over 4 pi E naught Q1 Q2 over R square times 1 over Q. That's this guy. This 1 over Q you are seeing is this guy that was here before. So, but this entire guy is force. So that's it. So once you have that now, you now have E equal to, one of the Q's can go, cancel out here. Yeah, because one of them is going to be, is exactly going to be the other one. So because two charges are interacting, so one of them must, be involved. So the idea is that one of them goes, and so And I've told you don't cancel out things. So one of the Q goes, and so what we are left with is 1 over 4 pi E naught Q. Just leave one Q over R squared. So the idea now is that you now have the formula for E. You can now write it as capital Q over 4 pi E naught R squared. So keep this one in mind. This is another, I'm going to call it Roman figure 3. So that is the formula for electric field. When you are talking about, how it relates to, when they give you radius and they give you charge, you can use this particular formula to find electric field. When they give you force and they give you charge, you use this particular one because this has, force over charge. So it depends on what you are given. You can always manipulate your formula the way you want to do it. So let's go to the next subtopic, electric potential. In some of the assignments I will upload for you, toy with these formulas, play with them, use them, and see how well you can use them. Then when we meet at interactive sessions, we can talk about corrections and problems you encountered, and then we can be good. But playing with them first is active physics. So, but establishing the knowledge is what we are doing in class right now. The electric potential, which is another important subtopic, has to do with, now, you must have heard of this concept of potential when we're talking about the gravitational field. It always has something to do with consideration of infinity. So we say the electric potential, but this time around is denoted by V. At a point is the work done in bringing a unit, as we always said, whenever we are considering stuff here in electric field, we use a unit positive charge, or we say positive test charge, a unit positive charge from infinity to that point in consideration, to the point being considered. So take note of that, to the point, to the point. Okay, it is measured in volts. Electric potential at the point is the work done in bringing a unit positive charge from infinity to that point. Let me make it that point. So it is measured in volt. Keep that in mind. And this time around, it is a scalar. It is a scalar quantity. It is not a vector. Now, I believe that as you're doing your physics revision for your exam, you should have a place where in your reading notes or your jotters, you have categorized what so far you consider to be scalar quantities and what you consider to be vector quantities. But either way, they're going to show up in your multiple choice or theoretical aspect of your exam. So that's just by the way. So now let's do it this way. Electric potential, let me write it like this. V equal to work done over Q. Excuse me. So, and we say it's measured in volt. So V equal to W over Q. And where we say V is electric potential in volt. Potential. So take note of this formula. This is like the first introduction here under the subtopic. So this is electric potential. W is work done in joules. Work done. Let me write this. Work done in joules. Then Q is charge in coulombs. So keep that in mind. So if we are to guess just a random unit for potential now, for to just guess a random unit, we would have just said joule per coulomb, right? Because up above here we have work done in joules, right? And then Q in coulomb. So one of the units for this is joule per coulomb. You see that? That's just keep that in your mind. It's just one of the units we'll consider for it. But as we go along, we have already established that it is measured in volts. So please keep that one in mind. So, but another, just secondary unit. The primary unit, when we say primary, the main unit is volt. So, but another secondary unit is what? Joule per coulomb. This is how physics works. You just have some, SI standard ones, and you have some other ones. So, but then we move on to making a substitution. We can prove to ourselves right now that we can show that V, or let me do something. Let's make a statement for now. For now, let's make a statement and say, okay, even this electric potential, V, the electric potential, where we are considering, or let's say the electric potential, the potential at a point due to a charge. So we want to give that formula now in terms of charge and radius. So the electric potential due to a charge Q at a distance. So this is just, I want to state a variation of the formula. So this is for you to take note of now. The electric potential, the point due to a charge this at a distance r from the charge. The charge is given as V equal to Q over 4 pi E naught R. Take note of this. So this is another, it's trying to say that, in cases where you're not giving work and charge directly and you're giving radius, so this is a useful formula to use. I'm going to call that Roman figure 5. So let's go straight into the next subheading. And that has to do with, okay, but let's make a point before let's note, if the work done is against, take note of these terminologies, is against the field. I'm going to mark against in red. If the work done is against the field, the potential is positive. So I'm just going to write it right here. I'm going to underline this one. But if the work done, that's 1 point. But if the work done by the field, if the work is done by the field. So there is against the field and there is by the field. Okay, let me take that to right again. There is by the field and there is against the field. And in the case of by the field, the potential is negative. Take note of that. In the case of by the field, it is negative. The potential at infinity is 0. That's another point. So please take note of that. Just like, and this is similar to the gravitational field. In the gravitational field, or for most fields, when you consider potential at infinity is always 0. So the potential at infinity is 0. So when you hear the one at infinity, you consider that to be what is 0. Take note of that. Put that in mind. Also, the potential of the earth is 0. So let's make that point. So in case you are asked in a multiple choice question or any other place, just keep it in mind. It's a very important point. Potential of the earth is 0. So keep that in mind. Is 0. The earth is used to test the potential of bodies. This is done by connecting wire from the body to the earth. The body is said to be earth. So when let me make this point in red. When you connect wires from a body, connect wires from a body to the earth. So you want to test for, so we particularly say it's used to test potential of a body. When you connect wires from a body to the earth in an attempt to test for charges in the body, in the body for charges in the body. Oh no, not just test for charges. You are testing to test the potential. In order to test the potential of the body. We say the body is earth. We say the body is earthed. So please take note of that. If electrons flow from the body to the earth, the body is a negative potential. You see this process, but when we do that connection, we now observe that electrons flow from the body to the earth. From the body to the earth, you have a case of negative potential. You have negative potential. So it is a negative potential. It has negative potential. So keep that in mind. Keep that in mind. If electrons flow from the body to the earth, it is of negative potential. So please take note of that. But in the other case, if electrons flow from the earth to the body, if electrons flow from the earth, electrons flow from the earth to the body, earth to the body, it is of positive potential. Take note of that. Positive points at higher potential than negative points at lower potential. Why negative points are at lower potential? Okay, so it's also worthy of note to say positive points have higher potential than negative points. Positive points are at higher potential than negative points. Just keep that in mind. Potential than why? Okay, let's put it this way. Why negative points are lower at lower potential. Keep this in mind. I think most probably the last thing we will talk about in this particular class before I am able to wrap it up is called potential difference. Potential difference. Take note of that. Right now, I hope that you are listening and that you are writing. There is no time for all those kind of, mesmerizing jokes or disturbing things. So the potential difference between any 2 points, in an electric field is the work done. Now, the thing with potential difference is that it is very similar. You will see some of the calculations, some of the definitions and calculations have a very close relationship with what we called electric potential. What we call electric potential in the first case, you see, if you scroll up here, we define something electric potential. You will observe that in that particular definition and the definition of potential difference, you will discover that there are very similar words. There's a very close, relationship. And then at the end of the day, by the time you are relating the formulas, you will get to discover that there is a relationship. But then the definitions are not the same. Don't mix up the point. Go and look back as you are reading, and making your jottings and your, readings. You will discover that electric potential is something on its own. Potential difference is something else on its own. So the potential difference between any 2 points in an electric field is the work done in taking now. This is the work done in taking a unit positive test charge, a unit positive. I'm not definitely. I can decide to put a test or not, but a unit positive charge from one point to another in the field, from one point to another in the field. Now, the difference that we observe here is that if you go back to the definition of electric potential on its own, you will discover that there is a mention of infinity in that particular one. But you don't see categorically the mention of infinity in the definition of potential difference. Now, the point here, please get it straight. The point here is that in electric potential, we are considering a test positive charge and with respect to infinity. But in this case, we are talking about two, let me underline it, 2 points. So in the case of electric potential, we are talking about a unit positive charge and from infinity to a point. So I'm going to say in electric potential, we are considering a point and infinity. The relationship between a point and then infinity. Then, but in the case of potential difference, we are considering two points, that two actual points. So there is no discussion of infinity in the case of potential difference. Now, this is clearly the difference between electric potential and potential difference. So these 2 points are actually real. They are real points, and none of them has anything to do with infinity. Not undefined. They are real, not undefined. So just get that as one of the first differences between these two things, because as we go on, you see a very great similitude between both formulas, but you have to establish that difference early on. So if a charge, let's dive into how the formulas will look on the long run. So if a charge Q is moved from a point at a potential V1 V1. Now that's like we are saying the first point is point 1. So we are moving a charge, because the idea of potential difference is that work done in moving a charge from one point to another. So if a charge Q is moved from a point at potential V1 to another point of potential V2, the potential difference is given by as the work done So because we have already stated it's not something like we are just making a random abstract inference. It's something like we are saying, because we have stated in the definition that it is the work done. So let's write that work done now. So we are now stating that, okay, if we have these things settled, that, okay, we have V1, V2 as the potential at those 2 points. Now, get one important point here. The fact that we said potential at one point and another point is trying to tell you that, oh, this is the idea. Electric potential. We're talking about now. Electric potential, you're talking about a point and infinity. But then we are saying, okay, for the first point, its own potential is V1. That is when you consider that point in itself. The relationship between that point and infinity, we call it V1. And then the relationship between another second point and infinity, we call it V2. Now, these 2 points have their own 2 electric potentials. These are the 2 electric potentials. If we now want to talk about the potential difference, we call that work done. And so that work done is defined as QV2. No, let's use V1. QV1 minus V2. So let me explain better by saying, okay, we have a point A and a point B, and the distance separating those 2 points is R. Now we have already established that, okay, the potential at point A or point 1 is VA, and the potential at point B or point 2 is VB. So if we have that, we've established that already, we know that generically, or will I say generally, in physics, work done is force times distance. Now, in this case, distance is like R, so you get force times R. And then we have already established the electric field formula. We said that is force, and I will practically say from equation 2 now, Roman figure 2. So from equation Roman figure 2, Roman figure 2, we have E equal to F over Q. Yeah, so that works. Then we now say, okay, if we make F subject of the formula from there, we have F equal to EQ. This particular, I think we stopped at Roman figure 5, so I'm going to call this Roman figure 6. If I put Roman figure 6 into, let me call this general guy now. Let me just call it star. If I put substitute 6 into star, so you'd have W, which is the work done, being written as EQR this time around. That's just straightforward algebra. That's math. So once you do that, you are fine, but we can still make another substitution. And the idea here is that we can substitute, I should have also established this guy, given it a particular, this one where we just defined, the formula for potential difference as work done, because it's practical work done of, in bringing, in moving a charge between 2 points. So now let me call this guy star star, this guy that we defined for work done, in terms of potential difference. If I call that star star, now look at the one we just established. I will call that guy 7. This one we just established by using equation 2 in star. When we substituted equation 6 rather into star. So we established equation 7. So the idea is that if you look at here, you see work. Here you see work. And I've told you most of the time, if you have attended my previous classes, you must have discovered that once we have something like this, work is equal to this, we can equate the right hand side of both equations. So equate the right hand side of star star to the right hand side of VII. So that's 7. So now the right hand side of star star, what do we see there? Q into bracket V1 minus V2. Or basically, since we are now talking about, because after I said it, I can say, okay, this V1, let's call it VA. So this is V1, V2, VB. So the idea now is that we have Q into VA minus VB. That's just representing first point, second point, equal to EQR. What did we just do? Let me point arrows so that you know what we are doing. We just equated this right hand side because that's work, and we equated it to this right hand side because this is also work. And this is not the first time we're doing something like that. So having established that, the next thing we can do is to, make, let's talk about this guy. Let's label this guy the potential difference. Let's call it, because this is the difference. This is the actual difference that we're talking about. You understand? That's the difference of the two potentials. So I'm going to say, okay, potential difference PD is equal to VA minus VB. So now if I do that, I can easily say, hold on. Yeah, so can easily say, okay, Q into PD equal to EQR. Now, these two Qs, they are the same, so they can cancel out. But I've always told you not to appreciate, not to do something like that. So Q can get out of the way. We're now left with ER equal to potential difference, right? So the idea now is that, okay, we can now say E, which is potential difference. Oh no, E, which is the electric field. E will now be P difference divided by R. In the big deal, we now have we can write this as V. Let's write this as, because we know that at the end of the day, because potential difference is a difference between two V's, it will still give us a particular V. You get? So let's write this as V now. We now have E equal to V over R. Take note of this guy. I think we have had something like that before, if I'm sure. Maybe not. So, but take note of that guy. That's another instrumental formula. I'm going to call it number VIII. So, and where, so the idea here is now that, but we already know what V is from, what E is rather. We know what this E guy is from. I'm going to go back to, and this is not something strange. You going back to formula labels, because you are going to have a lot of formulas in physics. You will have formula 200. So you'll be saying substitute equation 200 into equation 500. That's a possibility. So it's not something you rule out. It's not strange at all. So I'm going back to equation 3 up above here. You see it? This is where we first established a relationship between E and, Q and R. We said it. So I want to use 3 in this particular 8. This 8, Roman figure 8. So I'm going to say, see it, E is also here. So I'm saying substitute 3 into 8. Or better still, we are equating the right-hand side. So the right-hand side of the one up here, that's 3, is definitely Q over 4 pi E naught R square. So we'll come here and say Q over 4 pi E naught R square equal to V over R. Now the idea is on both sides in the denominator we have R. And just by basic math, you want to say one R cancel the other R, but I've told you not to take that approach. You don't need to put cancellations on your work. Just say, okay, maybe multiply both sides by R. So if I multiply both sides by R, multiply both sides by R, I am going to have Q over 4 pi E naught R left here and then V. So basically we can say another formula for our potential difference. Now this is not just potential, but this is potential difference, because this guy is equal to the difference between two potentials. And now we have found it also equal to Q over 4 pi E naught R. So take note of that. I'm going to call this particular one IX. That's like number 9. So now you will discover that I was telling you that in terms of formula and some of the words used in explanation, the potential difference formula is similar to the electric potential formula. So take note of what you are seeing right here. Q over 4 pi E naught R. And go back to the formula for electric potential. And you will see something similar. See it. So I can write that. So because please, this is R and it has always been R. That's the way I write my R. So but notwithstanding, you see that what we labeled as equation 5 is very similar to what we have down here as equation 9. But they are not the same thing. So I can write it below here now that equation 5 in your note, that you have the equation 5, which is electric potential. We obtain that to be electric potential. And those are not the only formulas of these things. Those things have variational formulas. So take note of all the formulas we have been running through. But I just want to pick out this particular concept and explain it. Equation 5, which is electric potential, seems similar to equation 9. To equation 9. But there are two different concepts. Equation 9, which in this case now is potential difference. Potential difference. And of course, they are going to run with the same unit. They are both potential, so they run with the same unit as volts. So let's go to another subtopic, and that is where we'll be talking about. This probably will be your first time hearing of the concept of electron volt. So let me quickly establish before I leave this particular concept, both having SI unit of volt, both having SI unit of volt. So volt and volt is small v. So keep that in mind. Let's go straight into electron volt, subheading electron volt, and that is represented with EV, E and then capital V. So that is electron volt. So this particular quantity, this is the quantity. This is a quantity of energy gained by an electron. This is the quantity of energy gained by an electron in accelerating through a potential difference of 1 volt, a potential difference of 1 volt. So keep that in mind. 1 volt. Now the idea is, for one electric charge, even if you don't know this before, get it established now. This can be fresh to you, but just know that an electric charge, if you want to define an electric charge in terms of its numerical value, an electric charge, and when we say an electric charge this time around, let me not write it as electric, an electronic, because when we come to the idea of electron volts, we are not just referring to any charge. It's not just positive charge or something. An electronic charge, and the idea here is that an electronic charge, be it positive or negative, the magnitude, the value, electronic charge is of this magnitude. When it's now electron, it is negative. When it's proton, it is positive. But this is the charge. This is it has the value of 1.6 times 10 to the minus 19 coulomb. That is the charge. So when you say 1 electron volt, it is kind of telling you that, oh, this is actually 1.6 times 10 raised per minus 19 coulomb times 1 volt. That's why it says the concept here is that it is the quantity of energy that has to do with 1 volt potential difference. So when you are multiplying it, you are doing electron, that's this value, and then this volt here is always 1 volt. So we are saying that, oh, the unit, how we form this unit to say 1 EV now be equal to, by the time you do this, whenever you multiply coulomb and volt, you have energy, and that energy gives you joules. So you're having 1.6 times 10 raised per minus 19 joules. So get that in tune. The energy acquired by a charge, a charge particle accelerated by an electric field in a vacuum, depends only on its charge and potential difference through which it falls. I mean, what we are trying to say now is that, okay, this EV, just keep this one in your memory, that 1 EV equal to this amount of joules, and this is the definition of electron volt. The quantity of energy gained by an electron in accelerating through a potential difference of 1. So keep that in mind. And so now the last thing we'll do is now relate kinetic energy to, we're going to relate kinetic energy to the, let me do it this way, to the centripetal force. Yeah, I want to relate, let me do it this way. I want to relate spinning, the movement of an electron, a spinning electron. Hold on, give me just a minute. So we have a case where we are talking about if an electron, so let me point this scenario to you. If an electron moves in a circle of radius r. Now, this concept I'm about to talk about was how it is the same picture where we talked about centripetal force when we were talking about gravitational field. And that idea there was a satellite moving in an orbit. So now I want to talk about an electron moving in a circle of radius r. So I want to introduce, the first here will be centripetal force, and centripetal force is mv square over r. So, but we know that, if we are to talk about the force of the electron itself, that's Q1, 1 over, we already established this, 1 over 4 pi E naught, Q1, Q2 over what? R square, right? Now, the idea here is that when we have just a single electron, this Q1, Q2 thing becomes Q square. So when you have the same charge, so Q1 equal to Q2 for same charge. So let's write that down. So when you're talking about the force, so for same charge, Q1 equal to Q2 equal to Q, then you can write it as Q. Just write it as Q. So I can now write this formula as F equal to 1 over 4 pi. This one is centripetal force. This one is already centripetal force. So keep that in mind. Sorry. So I can now write the formula as 1 over 4 pi E naught Q square over R square. Now get that clear. Now if I want to equate this is Coulombic. We know that this is Coulombic force. If we equate this Coulombic force to centripetal force, the right hand side, we have mv square over r. You go what's happening right here? Equal to, hold on, I'm coming. Yeah, hold on. Give me a minute, please. Force of attraction, this, okay. All right. So, mv square over r, that's this, okay. So let's establish some things here. So that force is equal to mv square equal to I'm coming. Give me a minute. Let me establish something. In the former, the when we are considering this, sorry, excuse me. Yeah, the idea is to utilize this. Okay, very good. Yeah, so let's not just equate the forces. What has to be equated is, let's do something about work. Let's do something with relating it to work. So now we've established, or let's say, okay, kinetic energy. Hold on. When electron is in motion, let me write. When electron is in motion, its kinetic energy is 1 over 2 mv square. Then if the electron moves in a circle of radius, the force towards the center is centripetal force, and it is provided by a force of attraction, this. So yeah. So if we were to do something like this, come on. Yeah. From this from the centripetal force, from centripetal force, F equal to mv square over r, abi? So mv square is what? Fr. So if I put that mv square here now, ke is what? Half fr. So just get that out of the gist first. So and this is centripetal force. So yeah. So anyways, I'm going to just conclude here. But just know that at a particular junction, we'll have to use this concept of, let me see how I can first establish. Mm, Come in. Give me a minute. Yeah, let me just keep this concept in mind. Just keep this concept in mind. But then have I already established KE, KE, KE? Yeah. I didn't use KE. Yeah. So that's fine. Center better. So hold on for a bit. Let me I want to relate the same concept we used for the gravitational centripetal idea. I want to relate it here. Hold on. This concluding parts. I want to make sure that I make them rhyme. Hold on, you can catch a breath here. So when I was talking about the gravitational, let me just go back to my notes on that. I was talking about the gravitational concept. I had yes, I equated them and I'll put it back into here. And I put mv square back into this. So yeah, I'm going to do the same thing here. So I just wanted to make sure I'm doing the same thing. So let's do this. Let's equate them first. So we can, yeah, sorry I have to do that, but you can ignore this part. Sorry. You can ignore this entire part. Let's not do, that's not what we intend to do. I want to do exactly that same relationship. So what I do is equate the centripetal force to the Coulombic force. Yeah. So let me write that. Equate centripetal force to the Coulombic force. And doing that means that you are doing the right hand side, because this is the centripetal force right here. And so we're equating the right hand side to the right hand side of the Coulombic force that I just established here. So that gives me, if you have that on your note, that's mv square over r equal to 1 over 4 pi e naught q square over r square. Now my intention is to now get mv square from here. So, but sorry, my screen kind of went off. Then I'm going to have to share Gonna have to share again. So gonna have to share again. So normally you say R cancel R, but I've told you not to do that. So you can say multiply both sides by R, and then you have mv square equal to 1 over 4 pi E naught Q square over R, right? So what does that yield? What does that give me? When I now consider kinetic energy, I know that kinetic energy is half mv square. I cannot plug in mv square here. This is the value now. So it gives me kinetic energy. I can now have, for an electron rotating around somewhere, you have 1 over 4 pi E naught Q square over R. So the kinetic energy is basically 1 over 8 pi E naught Q square over R. Take note of that. So this is kinetic energy. So keep that in mind. We've established that. Yes. Oh, better still. I'm coming. Yeah. So yeah. So just take note of that for now. We'll establish more concepts. When we start solving problems and we start doing stuff, you'll get to understand more and more of this. So let's wrap it up for today's class.